Okay, so as today's last lecture, it is about unmute म्यूट कर लें जिनका अनम्यूट हो गया. Yesterday we derived Schrodinger's equation for time independent as well as time dependent case, and today we'll see how we use this Schrodinger's equation to study case of particle in a box. If we have a macroscopic particle, big particle, then we use Newton's laws and we use equation of motion, which is F equals to ma, and we analyze our problem. Here we have subatomic particle, we have electron which is confined, or we have any particle, small particle, subatomic particle, which is moving along this direction. It is one-dimensional case, because three-dimensional is little complicated. Then we have to deal with partial differential equation. So you do not understand how we solve partial differential equations. So that's why we are keeping our problem very simple, and we are saying that it is 1D problem, particle in one-dimensional box, so that we have ordinary differential equation to solve, or our Schrodinger equation is a ordinary first order ordinary differential equation which we know how to solve. We can easily solve 1D, or we can easily solve ordinary differential equations. So this is my particle, and it is confined to move within this box, and I'm showing it by this wave because this particle is microscopic particle. This is very small particle, subatomic particle. It has dual nature, dual characteristic. It has particle as well as wave characteristic. So due to its wave characteristic, we say that wave associated with this particle has wave function psi. Okay, and it is function of, because position is only along this direction, position and time t. And we are interested in knowing this or finding this wave function for our particle so that we can predict dynamics of this particle. So our problem is we have mass, or we have particle of mass m, and this particle is moving here, and potential in this region where it is moving is 0, means no force is acting on this particle. It is free to move within the box, and potential at the walls of the box is what it is, infinite. And where are these walls? These are at these positions, that is x0, and another is at x equals to L. So dimension of this box, it is one dimensional box, and that dimension is what it is, L. It extends from 0 to L. As potential at the walls tends to infinity, means particle is confined within the box. It cannot move outside the box. So that means probability of finding particle within the box is 1. So it is confined to this box. Then we can, and this wave function of this is, because we are keeping our problem very simple. So we are ignoring time dependence of this wave function. So we can write this wave function as product of two functions. One is function of x, that is position, another as function of time. Let me write it as this. So this is mathematics. This is when we deal with partial differential equations. So I'm not touching that part, but just to give you idea. So we'll be solving only this part, or we are interested only in this part of the wave function. So we do what? We write only, we solve this for only position dependence of this wave function. Okay, so we are dealing with time independent wave function. This wave function is now what? It is independent of time. So we should write wave equation, or we should write which is called Schrodinger's equation for this particle. So that we have what? We have equation of motion, and we can write that as, we know it is nothing but law of conservation of energy. It is kinetic energy. Now in the form of operator, we can write this is kinetic energy operator d square over dx square, plus we have potential energy operator, and this is called Hamiltonian operator, operating with this operator on wave function, which is function of only position, which is time independent wave function, gives you, this is total energy operator, operation of this on wave function side. This is nothing but this is time independent Schrodinger's equation. Okay, and we solve this time independent Schrodinger's equation. And before going how we solve this Schrodinger's equation, let us simplify this equation. You have a 3D general differential equation if I write for you. So then we have here del square. But as we are keeping things simple, so we do not write del square here. Okay, so what we have in place of del square, I have one dimensional operator, that is double derivative of a function with respect to x square. Okay, so we can simplify this, and I can write this as, let me write this is by, this is d by d square of psi, plus if I shift this to this side and then I do simple mathematics, I can write it as 2m over h bar square. This is E minus V psi equals to 0. This is simplified version of this Schrodinger's equation. Okay, so we are applying, and this is mass of our particle, energy, this is potential, this is wave function of this wave associated with this particle. And if you see, this is what? This is second order ordinary differential equation. This is second order ordinary differential equation. Second order. Okay, we can solve this second order ordinary differential equation. We have techniques to solve ordinary differential equations. इसीलिए हम यहाँ पे ऑपरेटर d double derivative of, or this is total derivative, double derivative of psi with respect to x. So that's why we have simplified our problem to this. We have taken only time independent wave function, so that we need not to differentiate this wave function with respect to time. Another thing is we are studying 1D because we do not want here derivatives with respect to y and with respect to z. Under these conditions, we have reduced Schrodinger's equation, which otherwise is a partial differential equation. We have reduced it to 1D problem, that is, or to ordinary differential equation problem. So more simplifications are what? We said that particle is in a box where potential is 0. This is our assumption. These are assumptions. So under that assumption, we can further simplify our differential equation by putting v equals to 0 here. So then for free particle, this is condition for free particle when there is no force acting on the particle. So for that particle, we can write Schrodinger's equation as d by dx square, d square over dx square of psi wave function plus this is 2m h bar square, and this is only E now. V is 0 equals to 0. Boundary conditions you see from our model. This is model for particle which moves in 1D 1D box, one-dimensional box. So we can see that at this ball potential is infinite. It will experience infinite force at this ball, so it cannot move out of this. So we can say that wave function at x equals to 0, wave function x equals to 0 is 0. This is our first boundary condition. We have another boundary condition that is for the other boundary, other wall, that is at x equals to L. Again, potential is infinite, so there is no probability of finding particle at that boundary. So these are two boundary conditions. So with these two boundary conditions and this ODE, one ordinary differential equation, second order ordinary differential equation, we can solve this, or we can find different energy states, we can find different wave functions associated with this particle when it will be in different states. So it is in minimum energy state, or we excite this particle to higher energy state, what energies it will possess. So all those things can be, we can analyze all these things if we know how to solve this ordinary differential equation. And by solving this differential equation, I can write wave function as function of position, time independent wave function. So solution of this means writing wave function with these conditions, these boundary conditions. So I can further simplify this by putting this equals to some k square. So if I put this equals to some k square, then I can write differential equation as this plus k square psi equals to 0. So I can see that this is much more simplified version now, and we can solve this now. If you see what this k is, this k square is this thing, that is 2m e over h bar square, or this k is, this is under root, or let me do what, let me say that this k square times h bar square is equals to 2me. Okay, and if I shift this to left hand side, 2m to left hand side, you see that this is h bar square k square divided by 2m. Okay, total energy is what it is, kinetic energy here. Okay, so we can write it as potential is 0, it is 2p square over 2m. And if I compare this with this, so p is here h bar k. So then k, I can write it as h bar, sorry, p divided by h bar. What is h bar? H bar is h divided by 2 pi. Okay, so this is what, this is 2 pi p over h. And we know de Broglie wavelength lambda is h divided by p. Okay, and that means I can write k is 2 pi over lambda. So k is nothing, it is what it is? Wave number, 2 pi over lambda. This is wave number. This is wave number. Okay, so this we can solve now. This is my Schrodinger's equation, which I have written in the form of second order ordinary differential equation, just to uh, find wave function psi by solving this second order ordinary differential equation. And we know we write auxiliary equation. I hope you remember this. Plus this is k square. R is nothing. It is what it is, real or complex number. If you remember, we assumed solution of this type. It is e raised to the power r x, and then we substituted this wave function in this, and we get this auxiliary equation equals to 0. Okay, with this e raised to the power rx here, and we said that this decay is slow as compared to this, and then we say that this is 0. Or I can write from this that r square is minus k square, r is plus minus iota k. So I can write my solution. My solution as wave function psi is, if I write straight away, it is a arbitrary constant times cos kx plus it is b sine kx. Okay, so for this particle which is confined to this 1D box between these walls from x0 to x equals to L, wave function associated with this particle which is confined to this is in this form. It is a cos kx. We understand what k is, and it is b sine plus b sine kx. We have these arbitrary constants a and b, and we can find these arbitrary constants by applying these boundary conditions. So if I apply first boundary condition on my wave function psi, so I know wave function at x equals to 0 should be equal to 0. So if I put x equals to 0 here, wave function should be equal to 0. So let me write wave function at x0 is a cos of 0, which is 1, plus b sine of 0 is 0. This should be equal to 0 because wave function at x equals to 0 is 0. So what it gives you? This gives you that a is 0. Okay, so that means my wave function psi, this is from first boundary condition. So wave function psi is represented by the second function, that is b sine kx. Okay, so we apply second boundary condition to know what b is. So my boundary condition is that at x equals to L, if I put x equals to L here, again it should be 0. Wave function is 0 and the second boundary as well. So I can write this is 0. So b sine k L should be equal to 0. B cannot be equal to 0. We do not put this because already A is 0. If I put B also equals to 0, that means I am getting what I am getting, no solution, or I am getting trivial solution. So I am looking for non-trivial solution, meaningful solutions I am looking for. Then wave function psi will be 0 for all x values. Particle is nowhere. So we can say that this is not equals to 0. So sine kl is 0. From second boundary condition, we get this. And sine kl is 0 means for all k L equal to n pi, sign is 0. Okay, so wave number or k, this k is n pi over L, and k square is n square pi square over L square. Okay, and we know what I know, that k, I have assumed what k is, or k square is this, that is 2me over h bar square. So I can write this is 2me over h bar square. Okay, and this I write as E subscript n, because now energy is function of what? It is function of n, because here what is varying? It is only n, because n is what? It is integer, which varies in integral steps. So it is 1, 2, 3, and so on. And the rest is what? It is mass is constant, h is constant, everything is constant. I can write energy En, which is function of n, or I can write this as n subscript n, because this is not continuous variable. R is what it is, discrete variable. So you get discrete values. You get discrete values for energy. So it is what it is, n square. Let me shift h bar to this side. So it is h bar square. I already have pi, so it is pi square divided by, let me shift this as well to right left hand side, it is 2m. I already have L square there. So this is what, this is expression for energy of this particle. And this energy is what it is. It is depending on n. For different n values, we see we get different energy states. For this given particle, which is confined to move in this box of length L, we are not varying L, it is fixed now. And mass of this particle is fixed, everything is fixed. Only thing which is varying here is, if I give energy to this particle, it will be in different energy state, having more energy, and those energy states, possible energy states, are what? Corresponding, they are energy states corresponding to different n values. So we can see that we have, because you can, we can put all these values here and we can see what we can write. So it is corresponding to, or you can say corresponding to n equals to 1. You can write this energy, that is E1, and E1 is square of 1 is 1, it is h bar square pi square divided by 2m L square. Similarly, for N2, n equals to 2, E2 energy in the excited energy state or higher energy state, it is 4, n square is 2 square is 4. This is h bar square pi square divided by 2ml square. Next energy level is corresponding to N3. It is 9 h bar square pi square over 2ml square. So you can see here, this is 1 times this vector, 4 times the same vector, 9 times this vector, and so on, and so on. So E is proportional to square of n here, and you can see that if I draw it here, so this is my first energy level, this is my second energy level, E2, and separation between these two, that is delta E, you can say, is equals to, you can see this is 3 times E1, 3 times E1. Okay, because E1 is this h bar pi square over 2ml square, and E2 minus E1 is 3 times the same thing, that is h square pi square over 2ml square. And you can see what is energy difference between E3, this is E3 energy level, and E2. So if I see energy difference between E3 and E2, so you can see it is 5 times E1. It is 5 times E1. So this difference is 3 times E1, this is 5 times E1, then you get 7 times E1, energy difference between fourth and third energy levels. And it goes on increasing, this energy gap or energy difference, it goes on increasing. Now we can write our wave function. This is about energy. We are interested in writing wave function for this particle, which is confined to a box, 1D box, within which it is free. It is a free particle. I can write wave function here. Wave function psi is represented by now harmonic function, sine harmonic function, and it is periodic. As you can see, sine is periodic. So wave function is periodic for this particle, and I can write wave function psi. Again, it is what it is, different at different energy levels. It is what it is, b sine k is what it is, n pi over, we have written k somewhere here. It is k is, yes, you can see that k is, it is this, it is divided by L. So this is my k. So I can write n pi over L and x. So this is wave function. Okay, and B is still unknown. And if I
Sir,
yes.
सर एक चीज बोलनी थी. विशाल 121 रोल नंबर एंड 123 रोल नंबर अपना कंप्यूटर साइंस का टेस्ट सबमिट कर दो, मैं वेट कर रही हूँ, और जल्दी कर दो प्लीज.
Okay, I can find this B by using normalization condition. जो हमने कल भी बात की थी, normalization condition here is that particle is confined to this box only, and probability of finding particle within the box is 1. So if I use that normalization condition, so I know that probability density is this and dx. So this is probability within this small region dx, and if I integrate it from 0 to L, that means I'm taking the whole box, then probability of finding is what it is, 1. So let me use this normalization condition to find B. So I can write integral of psi square, wave function here is b square. I can write that outside integration. It is b square sine square n pi over Lx dx, and integration from 0 to L to include the whole volume of this box. And now you can integrate, and you know how to integrate. Sine square theta can be written as 1 minus 2 theta divided by 2, and then integrating that, I can write that as b square divided by 2, and this is integral from 0 to L. This is 1 minus cos 2 theta, so it is 2 n pi over L, and whole divided by 2, that 2 I have written out, this dx with x dx. This will give you 0 because this will, integration of this will give you sine 2 n pi over L, and when I put n lower and upper limits, substitute in this function, this will be 0. Okay, and we have left with 1, and integration of 1 with respect to x is x. I can write this wave function is so I can write this is b square over 2, and this is x with the limits from 0 to L, or this is equals to 1, and So this is b square over 2 times L minus 0 is L is equals to 1. Or I can write now b is, if I shift everything to this side, it is under root 2 over L. This is b. So let me put this value of b in my wave function psi here. So I can write this wave function as under root 2 over L times sine n pi over L x. So now this is a wave function which depends on both. You can see that it is what it is different for different n values. You have different wave function, different energy states. A particle is in different energy states. So wave function psi is function of this discrete number, okay, discrete variable, and this also depends on this x, which is continuous variable here. So that's why it is continuous function of x. So we can see, we can plot this wave function. You can plot it here because you can write psi1, that is wave function of the wave associated with particle when it is in lower energy state or in the first energy state or the lowest energy state. Then you can write a wave function for the particle when we excite it from this state to some excited state. I'll be writing wave function then. So that is for corresponding to n equals to 2. If that excited state is represented by n equals to 2. So we can plot these wave functions. This is function of x. So I'm plotting this. This x goes from 0 to, this is x0 and this is x equals to L. I'm plotting wave function along this axis here. So you can say that this is my state 1. So corresponding to n equals to 1, I can write wave function 1 as function of x. I can plot this wave function. So wave function psi1 of x is under root 2 over L. This is sine, n is 1 now, so it is pi over Lx. Now it varies with what? It is, we have fixed n and it varies with x. For different x values, you can see what is wave function psi1. So this value of x is L by 2. This is the middle of this box. So you can see this is L by 2. Here x is 0 and here x is L. So I have 3 values of x, and corresponding to these 3 values of x, I can find what is psi1. By plugging x0 here, I see this becomes sine 0 and wave function is 0. So this is my first point. And corresponding to x equals to L, if I put L here, L goes with L and it is only pi, sine of pi is 0, again wave function is 0. If I plug in here x equals to L by 2, then it is pi by 2 times L by 2. L goes with L, it is pi by 2. Sine pi by 2 is 1. So we have what we have, maximum value amplitude is under 2 by L of this wave function here. So we can plot this like this, goes like this. This is what? This is wave function. This is wave function of matter wave associated with this particle, which is confined to a box of length L in its minimum energy state. Okay, then you can plot it for the next higher energy state, that is corresponding to n equals to 2. That state is represented by this, that is n2. And then wave function can be written corresponding to n equals to 2. I write wave function psi2 as under root 2 by L. This is sine, now it is 2 pi over Lx. Again, I have fixed n, but wave function is now function of x. It varies with x. So you can see again, this is my point 0, x is 0 here, x is L by 2, this is x equals to L by, sorry, this is L, and I can write this as L by 4, and this is 3L by 4. I have divided this into 4 quarters. Okay, so you see by plugging in different x values, x0 and this, you see this is wave function. This is how wave function varies with x in its this state, that is second excited state. Particle is in this state, higher energy state, corresponding energy is this. This is the corresponding energy. When particle is in this energy state, wave function is this, and it is given by mathematically this, and graphically how it will vary. Okay, and then you can also plot psi square, and when you plot psi square for different energy levels, it is also function of x. So you see what जो भी negative wave function था, square of that will be positive. So this will get inverted. This thing here, this will remain as it is, but with different amplitude or different maxima here. Okay, but then we have 3D box. We can, as I said earlier, because it is difficult to solve ordinary, difficult to solve partial differential equations where we have partial derivatives are involved. So we can directly give you how this is what we have discussed. Okay, so you can see we have drawn it up to third energy state, and this is associated probability of finding particle. So probability is never negative, it is 0. These are the points where we can say that probability of finding particle in these states is 0. And it is always, boundary condition is always satisfied. You can see my wave function is satisfying boundary conditions. Wave function is always 0 at the boundaries. It is like a standing wave here. Standing wave conditions, if you can see this. And we have this is what we have done in case of the हमने semiconductor physics किया था. We solved this, not solved, but direct result was given. States in that case space. So now you have to solve it. Is that the thing I was discussing? It is now function of all the 3 variables. It is not only depending on x wave function, but still we are dealing with time independent wave equation. Time independent Schrodinger's equation. Wave function is what it is, time independent. Time dependence अगर आप देखेंगे तो then you will see oscillations at a given position. So this is product of, you can see this is product of 3 functions. This is function, wave function, you can say, which is depending only on x. This is wave function which depends only on y, and this is wave function which depends only on, so we assume our wave function as product of 3 functions, and these 3 functions are functions of only x, only y, and only z. And then we have a technique which is called separation of variables technique. I do not know how much mathematics you are doing. कुछ अपने कोर्स में अभी भी किया होगा, बट मुझे नहीं लगता कि पार्शियल डिफरेंशियल इक्वेशंस आप करते हैं. तो दैट्स व्हाई हमने इसमें डायरेक्ट रिजल्ट आपको बताया कि दिस एनर्जी जैसे हम वहाँ पे सॉल्व कर रहे हैं, वी कैन सॉल्व इट फॉर डिफरेंट वेव फंक्शन, एंड प्रोडक्ट ऑफ दीज डिफरेंट वेव फंक्शंस is our function psi, which is depending on all the 3 variables. Then we can write this is energy for this particle. Now particle is not confined anywhere, it is confined in a box cube. It is in a cube, you can say. Faces पे there is a restriction on this particle. It cannot move out of this cube, and it experiences infinite potential at these faces, 6 faces. So these the boundary conditions can be, we can frame boundary conditions, or we can see what are the boundary conditions if we understand geometry of this cube. Okay, and And rest is what it is. We get similar by applying boundary conditions. We get to condition on these wave numbers. Okay, so now you can see it in previous case how k is varying. You can check that it is n pi over l. So for all these जो भी हमने wave functions draw किए उनके लिए it is, you can check it from there that it is n pi over l. Okay, so I think this much is enough. बाकी बहुत कुछ है इसमें. We can find expectation values. We can talk about. So let us keep it simple up to here. Quantum mechanics is a big branch of physics, and in a small chapter we because फिर ये थोड़ा और complicated हो जाएगा. We can talk about different tunneling effects, this and that. So no need to. So this is all about your engineering physics course. You have from Monday onwards you have your end semester exam, and for that if you have anything, let me give you a little idea. Now it is 2 hours exam, online exam. Duration is 2 hours. Weightage of this exam is it is 50. Okay, so half of जो आपने अभी तक किया, that is 30 for mid semester exam, 20 for internal class tests and internal assessment, and 50 weightages, 50% weightages is for this exam, that is end semester exam. तो बहुत कुछ डिपेंड करेगा how you perform in this exam. You work hard. आपको मिड सेमेस्टर का you have experience of mid semester exam. Same or even similar things will be asked. Numericals will be like जो mid semester में जैसे numericals थे, that will be the percentage of numericals. Problem based questions will be there. Logical ability, आपका जो concepts हैं वो clear होने चाहिए. Straightforward questions will be very less, जहाँ पे आपको सीधा पूछा जाए कि derive this on. जो सबसे बड़ी प्रॉब्लम थी आपके मिड सेमेस्टर अटेम्प्ट करने में, दैट इज व्हाट दैट यू आर अटेम्प्टिंग इट लाइक आप सोच नहीं रहे हैं, यू आर डूइंग व्हाट इफ यू हैव डन आइंस्टाइन्स कोएफिशिएंट्स, सो यू आर डूइंग डेरिवेशन ऑफ आइंस्टाइन्स कोएफिशिएंट्स. सो दैट वाज नॉट आस्क्ड. इट वाज आस्क्ड दैट इफ b12 is equal to b21, है ना, तो देन यू वर आस्क्ड कि what was it? It was about population inversion. There was some. Yeah, I can. So,
Yes.
It was about that. So, बहुत सारे maximum students, they have done what? They started deriving relation between Einstein's coefficients, and उनको कुछ भी marks नहीं मिल पाए हैं क्योंकि बिल्कुल ही irrelevant हो गया वो आपका आंसर. You should write to the point. You should know what is asked, and you should try to attempt the question according to जो भी पूछा गया. Not go उसका कोई फायदा नहीं. You are wasting your time then. And numericals में भी ऐसा है कि बहुत सारे लोगों को numerical में ये नहीं पता लग रहा है कि what formula should be used. I'll share all this with you. जब आप देखेंगे तो आप अपनी आंसर शीट में you'll be able to see. If it is asked that radiation matter interaction, different possible ways how radiation interacts with matter, that is asked in context to what is there in your syllabus. So you are writing number of things, they are not incorrect, but वो relevant नहीं. Compton's effect, if we start writing photoelectric effect, okay, all these are what they are. We can say that there is radiation matter interaction is leading to all these phenomena, but that is irrelevant here because you know what is there in your course, and वी आर नॉट आस्किंग एनी सच वेग क्वेश्चंस, है ना, तो हम आपसे टू द पॉइंट और आपके कोर्स से रिलेटेड ही बात पूछ रहे हैं. तो इन योर कोर्स, what how radiation interacts with matter according to what is your syllabus or what chapters, what concepts you have done. It was in light of that you have to explain, stimulated emission, spontaneous emission, laser में आपको सबसे पहले हमने ये बताया कि how light interacts with matter. These are the three basic interactions, है ना, जो हो रही. उसमें भी you should be very clear in writing your answer, and the best way of writing or best way of presentation, है ना, अपने आंसर को प्रेजेंट करने का तरीका जो होता है, that you should draw whatever you know. It should be, है ना, क्योंकि you know sometimes बहुत सारा लिखने के बाद भी उनको मतलब वो इफेक्ट नहीं आता है जो आप सिर्फ एक सिंपल सा छोटा सा डायग्राम ड्रॉ करते हैं where you explain everything beautifully, तो that gives you more credit. तो ऐसी कुछ चीज़ें हैं जो थोड़ा सा स्मार्टली आप अटेम्प्ट करें, और ऑल द बेस्ट फॉर योर एंड सेमेस्टर एग्जाम. प्रैक्टिकल्स आप दे रहे हैं और फाइनल एग्जाम आई होप दैट यू ऑल विल स्कोर वेरी गुड मार्क्स अबव ए. बट अभी जो मिड सेमेस्टर था दैट वाज नॉट वेरी गुड, है ना, वहाँ पे थोड़ा सा डिसअपॉइंटमेंट है. और कुछ क्लास टेस्ट भी आई विल शेयर विद यू. जो क्लास टेस्ट हैं वो भी आई विल शेयर. या तो आपका एंड सेमेस्टर जब खत्म हो रहा है, इट इज एंडिंग ऑन फ्राइडे, या उससे भी आगे भी एक्सटेंड कर रहे हैं. व्हेन यू हैव योर लास्ट एंड सेमेस्टर एग्जाम?
25th.
25th.
Yes.
ओके. सो 26th को या फिर 20 मंडे जो भी होगा उसके बाद, if it is 25th is what, it is Monday, what it is, Friday, it is Friday. तो Friday एक तो मिड सेमेस्टर तो आई विल शेयर टुडे विद यू. और फिजिक्स, इंजीनियरिंग फिजिक्स एंड सेमेस्टर एग्जाम इज ऑन विच डे? 21st को है. तो
21, sir.
Okay, then it will take a little time. So by 28th March I'll share with you your answer sheets of your end semester exam as well, corrected answer sheets. ठीक है, 28th तक, so that you can, आपके रिजल्ट आने से पहले आपको पता होगा मिड सेमेस्टर में व्हाट इज योर स्कोर इन क्लास टेस्ट एंड व्हाट हाउ यू हैव स्कोर्ड इन एंड सेमेस्टर एग्जाम. एंड यू आर फ्री टू डिस्कस विद मी इफ यू हैव एनीथिंग, इफ यू फाइंड एनी कहीं पे कोई अनचेक्ड रह जाता है, इफ यू हैव एनीथिंग, एनी प्रॉब्लम इन योर आंसर शीट, यू फाइंड दैट कुछ अनचेक्ड है, कुछ करेक्शंस नहीं हो पाई, या टोटल नहीं ठीक से है, व्हाटएवर, वी कैन तो वो एक हम दिन रख लेंगे. अभी तो आई विल नॉट डिस्टर्ब यू बिकॉज आप यू आर प्रिपेयरिंग फॉर योर एंड सेमेस्टर एग्जाम. सो आफ्टर 25th, लाइक ऑन एनी डे, लाइक 26th, 27th या 28th को ही ग्रुप्स में आई डिवाइड यू इनटू स्मॉलर ग्रुप्स, सब ग्रुप्स, so that we can interact and आपकी problems को ले लेंगे. So okay, if with this let us end here. All the best once again for your final exams, and work hard, do well, and if you have anything, any queries, anything to ask about final exams or about anything, you can stay back, ask your queries. And those who do not have anything to say, anything to ask, they can hang up.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.
एक्सक्यूज मी सर.
हम्म.
सर जो हमारे क्लास टेस्ट हुए तो आप उनका एवरेज लगाओगे या फिर जो हमारा बेस्ट होगा, बेस्ट मार्क्स होंगे उसी को ऐड अप होंगे?
अभी दोनों क्लास टेस्ट को इवेलुएट कर रहा हूँ मैं. ठीक है, मैंने पहले भी कहा था कि आई विल सी योर परफॉर्मेंस इन बोथ द क्लास टेस्ट्स, अगर मुझे ऐसा लगा कि किसी एक क्लास टेस्ट में बहुत बुरा परफॉर्मेंस है और दूसरे में कंपैरेटिवली इट इज गुड, तो आई कंसीडर ओनली दैट वन विच इज गुड। ठीक है, if I find that it is
सर हाँ लिया था सर पहला वाला,
yes,
कुछ इशू था सर, मैंने नहीं लिया था ना सर पहला वाला टेस्ट, हम मतलब कुछ इशू था उस टाइम, आपने आपने बताया था ना सर मुझे।
हाँ, अब जिन
मैंने
जिन
नहीं
लोगों
लिया
का
था।
जिन लोगों ने एक क्लास टेस्ट नहीं दिया होगा तो उनके लिए फॉर्मूला विल बी दिस, ओनली दैट विल बी कंसिडर्ड। ठीक है,
यस सर, थैंक यू सर।
वो चाहे उनका अच्छा हुआ है फिर चाहे बुरा हुआ है तो दैट विल बी कंसिडर्ड।
थैंक यू सर।
ओके बेटे।